Hello, this is Mr. White, and this video is on the mean value theorem for integrals, as well as the second fundamental theorem of calculus. Here are the two exercises for this video. And even though that first exercise doesn't explicitly say mean value theorem in it, it does say average value. And we know that in math, average and mean are largely synonymous. So we'll need to recognize that mean value theorem for integrals applies. Let's get this second one out of the way. And before we dive headfirst into that first exercise, let's bring the mean value theorem for derivatives or for differentiation, as well as the mean value theorem for integration onto the board at the same time. And let's make sure you see that these are just two different sides of the same coin, just two different interpretations of really the same theorem. So you should recall that the mean value theorem for derivatives had to do with the tangent slope equaling the secant slope, and I hope that all still sounds familiar to you. And a critical relationship here was that f prime was the derivative of this f function over here. And whether we called it f or not, we understood was not really crucial. So we could have been totally fine with saying that g prime over here and g over here, right? And we understand that as long as that derivative relationship exists, we can put a whole bunch of different things in here. So why don't we put little f and big F over here? That derivative relationship still holds, doesn't it? Little f is the derivative of big F. So this theorem still holds. And then if I were to multiply the b minus a denominator down here over to the left side of the equation, if I were to multiply the b minus a over here, I would still have a true statement. And now let's compare these two different versions of the mean value theorem. Notice that the left side of the mean value theorem for differentiation now equals the right side of the MVT for integration. And of course that means that this quantity over here must equal this quantity over here. And isn't that what the fundamental theorem of calculus states? So just in the same way that the FTC united the derivative and the integration half of the subject of calculus, we see that it also unites those two different versions of the MVT. So now that your mind is blown, let's go back up. So we are to find the average value or the mean value of this function over the interval and find all the values of x on the interval for which the function equals its average value. In other words, all the values of x that satisfy the conclusion of the MVT for integrals. And rather than focus on too much what exactly that all means, let's start by getting a sketch, and then we'll interpret these words here. So let's take kind of a pre-calculus transformation approach to this. Let's think of how y equals x squared, our parabola looks like this. And we should also then be aware that y equals x to the fourth looks kind of like a parabola, except its nose is a little bit flatter. It dips below the parabola for a little bit, but then it skyrockets upward, more like that. So that's our graph of y equals x to the fourth. And then we expand our focus and look at what effect the negative sign has. And we say, okay, that's just going to flip this graph upside down. It's going to look more like that. And then we expand our focus once again and say, what about that plus 16 in the front? If I look at that as negative x to the fourth plus 16, the plus 16 will just vertically translate this graph upward by 16 units. And if I take a look at the interval that we're supposed to be concerned with, I'll notice that the endpoints of that interval just happen to be the x-intercepts of this function. If I plug in a 2 here, well, 16 minus 2 to the fourth gives me 0. So that's an x-intercept. And same thing with negative 2 as well, right? So if I want to know what the average value of this function is on the interval from -2 to 2, I imagine two walls set up here at -2 and 2, and I imagine that this big block of ice right here, this is an analogy that I'm sure I've used in class, this big block of ice is melting, and it will melt to some level, some water level, and again, we're ignoring the fact that water and ice have slightly different densities. But when it melts, it'll come down to this level. And that area of the ice, we are claiming, will be equal to the area of this water here. And the height of that water, that's what we are calling the average value. And I'll just write that as F average. So let's write an equation for what was just stated there, that the area of the ice will be equal to the area of the water. The area of ice is just going to be the definite integral from -2 to +2 of our function, 16 minus x to the 4th dx. And the area of water, since we're dealing with just a rectangle there, is going to be the height of the water, which we said would be F average, times the base of the rectangle here, which I'm going to go ahead and write as 2 minus -2 rather than simplify it. And the reason is because I just really want to show that this really is all that the mean value theorem for integration is saying. I wrote F average instead of F of C. We'll get to that in a moment. But here is our A and our B values, -2 and 2. And over here we have B minus A, 2 minus -2. And of course over here we have the function f of x. So that's really all that the integration version of the MVT says, is that the volume of the ice, or area of the ice, equals the area of the water. In our 2D depiction here, of course. So let's proceed. Let's go ahead and evaluate that area of ice integral there. If I anti-derive the 16 minus x to the 4th there, I'm going to get 16x minus x to the 5th, and a 1/5 to balance it out, from -2 to 2. And if I want to isolate f average, I can bring the 2 minus -2 over to the left-hand side over here. And this is where you've probably seen in our textbook where they have a 1 over b minus a in a formula. And if you didn't know what that means, this is where it comes from. So instead of the b minus a, I'll go ahead and put 2 minus -2, or how about just 4. And if I proceed with the FTC, I will get this. And obviously you are free to check my arithmetic if you like. One of the things we're asked to do is find the average value, so I'll put a box around it. We've completed that part of the task. And let's think of whether this makes sense with regards to our picture. We scroll back up, and if we're saying that f average is at 12.8, does that make sense given the 16 value here? It seems reasonable given our sketch. So let's now turn our attention to the second part of the request here, to find all the values x on the interval for which the function equals its average value. And that's really what the MVT for integrals is concluding, is that there will be at least one point, and in this case we see 2 points, and if you didn't see that there, I'll emphasize it here and here, where the average value, in other words the water line, equals the ice contour, so to speak. So our job now is to find what are those two values. In other words, what's this x value down here, which I'll call C1, and this x value down here, which I'll call C2. And we can tell just due to the symmetry of the picture that C1 and C2 are going to be opposites of each other. So if we look at those two newly created points as points on that original f of x curve, then we could say that this 12.8, this average value, we could say that that is also, that same y value is also f of c, where c represents either C1 or C2. And just to be clear, that was supposed to be a horizontal line here, but it looks like a minus, so let me just turn it into an equal sign. We need to say that whether you call it 12.8 or f of c, they're one and the same thing. So that's the equation we need to solve. And when we solve this equation, f average equals f of c, we will get that c1 and c2 value. And now we see where if I scroll down and bring the MVT for integrals back up, now we see why it says f of c instead of f average. Again, it's really the same thing. So let's get this out of the way. And let's set f of c equals that 12.8 or 64/5. And f of c is going to be 16 minus c to the 4th power equals 64/5. If you instead just keep an x here and solve for x instead, not a big deal as long as you realize that that x represents the c values guaranteed by the MVT. And if I rather quickly go ahead and solve that algebraically, that would give me c to the 4th equals 16 minus 64/5. That's going to be 80/5 minus 64/5. And 80 minus 64 gives me 16/5. And when I go ahead and take the 4th root of 16/5, it turns out that 16 is a perfect 4th power of 2. So that would give me c equals just 2 over, now 5 is not a perfect 4th power, so I either put 4th root of 5 or 5 to the 1/4 power. Since I'm taking an even root here, and also given the clues that we saw in the graph, I'll put the plus or minus. And that equates to decimal approximations of plus or minus 1.337. Put a box around it. We've just found the values that are guaranteed by the MVT for integrals. If I want to get some graphical affirmation here, I graph the original function and that 12.8 average value that we calculated. I take the area under the ice, in other words, the original function, and I see that the area is 51.2. I take the area under the water, and I see that the area is 51.2. So that checks out. And furthermore, if I keep scrolling, I have the screen capture here of where I intersected those two curves, and I see that yes, indeed, there's an intersection at 1.338, and I can just tell visually that there's another intersection at its negative 1.338. All right, that's the MVT for integrals. Let's go on to the next exercise. So in this exercise, we are to integrate the expression on the right to find big F as a function of x. And then we're supposed to demonstrate the second FTC by differentiating that result. Let's focus on part A first. And rather than just dive into some calculus processes, FTC and such, let's try to get a real understanding of what this means and what this looks like. So take a mental snapshot of this function of t and going from 2 to x. And I'm going to bring up a GeoGebra construction here. And you see that I have the horizontal axis now is labeled as the t-axis. And here is my little f of t, cube root of t to the 5th power. And if I'm to integrate, do a definite integral from 2 to x, this is what that looks like. X is a variable, so it's allowed to slide along the t-axis. And the integral between 2 and x represents the area under the curve, right? So keep that understanding in mind. That's going to be rather crucial for really understanding the second FTC on a meaningful level. But let's go back to here and go ahead and find that integral now. We will, of course, start by rewriting this integral in a more calculus-friendly way. We'll rewrite it as t to the 5/3 power dt. We will antiderive t to the 5/3 and get t to the 8/3. And then we'll put the 3/8 in front to balance it out. And we'll go from 2 to x. And that will simply give me 3/8 x to the 8/3 minus 3/8 times 2 to the 8/3. And there's not really a whole lot I can do to simplify that. If you're really curious, this constant right here is a decimal approximation of minus 2.381, but I think I'll just stick with the exact value there. And that is our f of x expressed as a function of x. That's my weak attempt at putting a box around my answer, you see. And sure enough, if I were to just plug some random number in for x there into my calculator, in this case I've just plugged in 6, and plugging in x equals 6 gave me 42.195. And if I bring GeoGebra back onto the screen and I drag my x value over to 6, I see that sure enough I get the area of 42.195. So I trust this is all making sense at this point. So here's essentially what the second FTC invites us to do. It invites us to look at this function, this big F, which represents our area under the curve, as a function in its own right. So as I drag for different values of x, I see that that area is changing. Let's now ask the question, at what rate is this area changing? If it's a function in its own right, how fast is this area changing? Well, let's start by graphing big F. So I've got that built into my GeoGebra construction, and there you see that point that just appeared on the screen, that green point. Notice that right now when the area under the curve is about 25, notice that that's the y value of that green point F. As I drag to the left and I see that the area is 12.7, that looks like what the y value is for the green point F. So that green point F is keeping track of this changing area, this ever-changing area, and kind of get a sense of what curve it's tracing out. What does that function big F look like? Well, let's go ahead and turn the trace on in GeoGebra. And now as I go to the left and I leave a trace of all those values, I get a sense of what the big F function looks like, what the antiderivative function looks like. And the question we are invited to ask with the second FTC is, how fast is this changing? What's the rate of change of this function, big F? So let's actually go back and do part B and then further discuss the second FTC. So for part B, we're going to derive, we're going to differentiate the result in part A. And so let's say big F prime, or let me write it this way. Okay, d over dx of big F of x. We know that's the same thing as big F prime. And let's go ahead and differentiate this function over here. So if I differentiate 3/8 x to the 8/3, I get 1x to the 8/3 minus 3/3 gives us 5/3. And careful, the student is often sucked into a trap here of trying to do some fancy processes for differentiating that. But notice that that's just a constant. So what's the derivative of any constant? Well, it's going to be 0. So x to the 5/3 minus 0. And I don't even really need to put the minus 0 here, right? So we've technically completed this task. We've differentiated the result in part A. And as far as what do we write down to prove that we've demonstrated the second FTC, there's not a whole lot to write down, but you really just need to know in your own mind that you understand what the second FTC told us and how we can get what we can do in the future with the second FTC. You may have noticed that it felt like we did a step in part A and then we undid it in step B. We anti-derived in step A and then we derived in part B, and it felt like we just undid the work we completed. So let's understand that what the second FTC is telling us is that if you want to take this function, big F of x, representing that area under the curve, and if you want to know how fast that area is changing, you don't really have to do all this anti-deriving and then deriving. All you have to do is take this x value up here and plug it in to this function, and the deriving and the anti-deriving will cancel each other out. When you do, d over dx on the left and d over dx on the right, this d over dx and this integral essentially cancel each other out. They're inverses of each other. So all you do is you take the x, you plug it in for t, you ignore this constant down here, because remember, it went away when we derived it. And that is exactly the answer we got in step B. So now we know for future reference, when you're asked to do something like that, you don't even have to go through the anti-differentiation process. All you have to do is plug in the x into here and get your final answer. So let's go back to GeoGebra one more time and take a look. Since we were talking about finding the rate of change of that function big F, that green function big F, that's represented by the slope of its tangent line, right? The rate of change. So notice that the slope of the tangent line, that red line there, notice that it's adjusting as I go left to right. And what the second FTC is telling us is that the slope of that red line at any point in time is equal to the y value of this red point. I know this is heavy stuff. Try to get as much of it as you can, and we'll discuss further in class. But notice that the red point on the screen has a y value of about 15. That's a point that's on this original little f function. This little f also tells me the slope of this big F. Okay, that's my best attempt to try to clarify this via video. I hope you got something out of it. But again, we'll surely continue the discussion in class. And the last comment I have to say about this, I just can't resist trying to squeeze this point in. This is something that I think our textbook doesn't cover as well as it ought to. We should be aware of what happens when we don't have just an x up here. But what about when we have something like 4x squared, some other function of x? So if we try to do what I said the second FTC said we could do, if we take the derivative of the left-hand side, this time, for big F of x, the second FTC said we could take that original x and just plug it in for t. And we tried to demonstrate that in this preceding exercise. And we will do something similar here. We'll plug in, again, the derivative, the d over dx. We'll basically cancel out this integral, and we'll plug in 4x squared for t. So instead of t to the 5/3 power, I'll plug that 4x squared in here. But the one additional thing I must realize is that I have to apply the chain rule. So I have to, since we're deriving, that chain rule cannot be ignored. I have to take the derivative of 4x squared, that inside part, and multiply it and get 8x here. And then I can proceed to simplify my final answer. And if you really care, that turns out to be 2 to the 19/3 times x to the 13/3. But my bigger point here is just beware of the chain rule.